Okay. So when I'm at Brandeis, I make students come up all the way to the front. I'm going to try that because I don't think I can write big enough for you guys to see back there. So if you want to know, come. Yes, there are lots and lots of chairs down here. Yeah, try and move down. Yeah. So while you guys are moving down, I'll try and summarize the different things that I talked about yesterday. And what I'm going to try and break down are the different aspects of these Edwards ideas that we need to be aware of and think about. So if I didn't point this out clearly yesterday, one of the fundamental assumptions in anything like an Edwards ensemble is that these block states that we are creating maximize entropy. So one possibility could be that that's completely the wrong idea, right? It could be that these are some end states of some dynamics, and the dynamics completely controls what states we go into. Entropy maximization has no role to play. If that's true, and that is a perspective that is still being debated, whether dynamics controls these end states or it's an entropic principle that determines what these block states are. So when I say Edwards ensemble, put me in the entropy camp for now. So that checking whether that is true or not will depend on first constructing the right Edwards ensemble and then checking it, right? That is right. That's what I'm doing. But I'm doing entropy maximization subject to constraints, but even that's not necessarily true for granular systems, right? If you talk to Mathieu will say that, the jam states are end states of some dynamics. It has nothing to do with entropy maximization, right? Or if you look at, driven systems like charge density waves, etc., it's a completely non-equilibrium system. There's no reason to believe that entropy maximization has any role to play. So Edwards is, I think, the one sort of the zeroth level postulate is that these block states are chosen through their entropy maximum. So because of which block states I get is determined by maximizing entropy. So that now what these block states are, what are the right conserved quantities to associate with them, what are the constraints, those are all of the things we are debating. But we're starting from this assumption that entropy maximization plays a role, and that I think can only be checked through experiments. Because there's no fundamental equilibrium stat-mech postulate. So even in equilibrium stat-mech, right, that's a postulate. That's the fundamental postulate of equilibrium statistical mechanics. That there's something like an entropy, and entropy maximization is what determines what my states are. Yes, does that ring a bell? So that's a postulate, right? Just like in quantum mechanics, we have postulates, there are postulates in equilibrium statistical mechanics. So that's one of them. So that postulate we are holding on to here. And that can only be checked through experiments. Okay, but then what are the different things we talked about? So what I argued yesterday was that if there is a conserved quantity, and I guess I'm sure you guys can't see this, right? Can you guys see this back there? No. Yes? Back there? Okay. Dov told me he cannot see it. Okay. Then, under certain conditions, it is possible to define an intensive quantity like temperature. And what were those conditions? What was the condition that I needed to say that I can define an intensive quantity? I relaxed the equiprobability constraint, but I did need there was another requirement. So I said they're not equiprobable. The states can occur with some weights, but the weights have to be factorizable, right? So if I take two states and put them together, the weight of the joint state is a product of the weights of each state, right? So that was an assumption. So with all of this, if all of this held, then what I would say, and remember these are all for mechanically stable states, so the constraints, keep that in mind that these are constrained states, but for these constrained states then, and I said, the constrained states are then characterized by, so these are the block states, and they're characterized, so I'm going to put a B in there, are by the positions and the forces. So if the Edwards ideas are correct, then what I should be able to do is write this as proportional to e to the minus something over x, right? Now bear in mind that this Q can be some complicated object, and this doesn't have to be temperature, but this is the idea, okay? Now, even if I have that, right? Now if I say, so the analogy here is P equilibrium of particles is proportional to e to the minus beta E. Correct? This is the analogy we are doing, right? Okay. Given this is sort of basic in some sense, right? Then I have to work out what the partition function is. Another question I can ask, like if I have exactly solvable stat-mech models, etc., one thing I can ask then here is what is the probability of finding a particular energy, right? And what is that then? So this is each microstate. Now, I'm going to have this is equal to the density of states, e to the minus beta E, over my canonical partition function. Yes, everyone okay with that, right? Okay. So let me phrase it this way, that if I could calculate this in any stat-mech problem, then I've solved the problem, right? Because this is just an exponential of e to the minus beta E. If you give me the temperature, this is just a number, right? This is the complicated thing to calculate. And we don't calculate that because this is a difficult thing to calculate. We calculate the canonical partition function, if we can. Right? We try to as best as we can calculate the partition function. So what I'm going to say now is the challenge here is exactly the same, right? Even if this is true, right? Let's say that is, so I'll keep that question aside for now. If I want to know what P of Q is, because of this lack of equiprobability, then this Z micro was just a weighted density of states. And I have some, this is going to be divided by Z of X. Right? So either I could try to calculate this, or I could try to calculate that. So what I am trying to get across is that even if this is correct, calculating this is a non-trivial problem. Okay? So when I'm talking about the dimers, really what I am trying to point out is that even when I have identified, let's say, this flux, and I'll remind you guys of what this is, if I could figure out what the density of states is, how many states do I have at a given flux, then I've solved the problem. So all of the theories of dimers then focus on trying to computing that in some way or the other, right? So if I want to construct like a field theory or a coarse grain theory, then this is what we're going to try to focus on to try and compute. Okay? Okay, so what we will try to do today is I'll review quickly what the dimer problem is and what we know about it, and then I'll try to identify what this Q is for the granular problem. Okay? Any questions so far? Did any of you try to construct a dimer configuration that's all vertical dimers? Okay. And did you compute the flux? That there were many, many loops? Either there's one loop or there are many, many loops. There are two possible ways of doing it. So here's my vertical, yes. Okay, so I'm going to ask someone to tell, so you did it already, so you're not going to answer me. So if I say, let's say for some reason, I have put on a field on the system which prefers only vertical dimers, right? And then how many of those configurations can I create, and what is the flux is my question, right? So if I say I have to put, all of the dimers have to be vertical, let me put one here. What are the other possible, how do I proceed? So I'm guessing from, I don't know your name. Olofia, okay. So I'm guessing what you did was this one? Okay. Right? Yes, that's the one you did? So the alternating one, right? Yes? Okay, so let's do that, right? So for that particular one, Olofia says, and I agree with him, that the loops are all system spanning. So what do we want to do? Right, so I want to put 3 arrows on this, and this is coming in, so I have this going out, etc. Correct? So if you now want to follow one of these, it will just follow one. If I put this on a periodic boundary condition, it will be a loop that winds across. Okay? So that tells me that I have no local moves in this system. Right? There's no local moves allowed, which will keep me in the same flux sector, right? So the flux is a conserved quantity. We have talked about that. The flux is a conserved quantity. So the flux of this because these are all going to be going up, right? I have done this alternately. In some ways, it has a maximal flux. Does that make sense? Because if I draw something through here, right, nothing cancels out. Yes? So it has a maximal flux, and these maximal flux states, and this is a generic statement for all of these dimer models. The maximal flux states have the fewest possible moves that I can do to update them. Okay, so it's saying that in this flux sector, there's basically one state except for global translations, right? So the entropy of this sector, or the density of states of this sector, is 1. Okay, not the entropy is 0, the density of states of this sector is 1. Now I could do a different vertical dimer problem, which is also allowed, where I do the following. Now what will I have to do if I put all of those? And then the only ones I can put here are then, so there's nothing here, right? And this now has to go that way, right? So now the flux is going to be 0, because everything will cancel out. And how many loops do I have here? As many as plaquettes, correct? Right? So the 0 flux state has an exponentially large number of states, and the entropy is finite. Everyone with me here? Right? Because I can do, every loop can be flipped to give me another configuration in the same flux sector. Right? So two things that I want to point out. One is that these flux sectors are disjoint. So I take the full phase space of all of my dimer coverings. I cannot go from one flux sector to another without doing a move that's system spanning. And within each flux sector, I can ask either what this is or what the entropy is, which is the log of this, right? Sorry, omega is the log of, S is the log of this. So does it scale as n or not, right? So if this scales as exponential of n times some number, let's call it small omega, right? Then my entropy is, then I have a finite entropy. I have an entropy per site or per. Questions? Comments? Right, so what I'm trying to do here is trying to count the density of states by counting the number of updatable loops, right? Because those are the only moves allowed. So what we are arguing is that if I have these local moves that take me from one state to another and the same pi sector, then there are lots of states in that sector. Everyone okay with that? Okay. Okay, so I'm going to say something here, and I have to say at this outset that the dimer problem, I'm giving you sort of a very quick rudimentary analysis of it. It's been worked on, studied in the context of quantum dimers. That's how I first got to work on it. Classical dimers, all kinds of things, right? So I'm just giving you a very quick, but the idea is to say within this context, some of the ideas that were useful are useful for the granular problem, okay? So in this case, so ultimately what do I want to do? I want to try and construct some model for this, right? Which here is a model for that. Yeah? Now, this is what field theories do for you. If I can write down a proper sort of Gainsbourg-Landau or an action or something, if I can coarse grain it, then I know what this looks like for a field which sitting in a given pi sector. So here what I have argued is entropically then, and this is people like Sanath have talked about it, right? There's no energy here because every configuration has exactly the same energy. The constraint guarantee, I'm not talking about energy here at all, right? So the only thing that can favor a certain state over another is the density of states. If I have lots of density of states in a particular sector, I'm more likely to find it, right? So what this is telling me is that the smaller the phi, the more sectors I have, more states I have in that sector, right? So one, the free energy for these dimer problems is pretty well established to be this is the, with the constraint that the divergence of V is 0. Because if I now minimize this free energy, I'm going to get the minimal flux sectors. That makes sense? So this is just doing electromagnetism on a lattice. It's a lattice gauge theory if you want to use fancy language, right? So the B field is what we defined yesterday. And so what I'm trying to say is this coarse-grained theory reproduces the same results that I would get from the entropy argument. This is sort of a crucial thing that I want you guys to understand, because that's ultimately what we are aiming towards for the granular system, to be able to write down, and we haven't managed to do it yet, except there's a very recent paper that I'll talk about, is can I construct a coarse-grained theory of granular systems? Okay, now, and again, in granular systems, we are not talking about energy. We are only talking about some conserved quantity in these mechanically stable states, which are the constraint states. So in a very general way, the only thing that can matter is the entropy or the number of states in that sector. So what I'm trying to say is, if I fix Q, right? So this is the canonical ensemble. Let's forget about that for now. If I fix Q, then what matters is this, right? Or the other way of saying it is this part of it is sort of trivial. If I can figure how that depends on Q is the question that we are. So for example, in the dimers, I could say, you know, there's a bias that I put in, like a e to the minus beta e, which will favor certain states over others, certain Qs over others. That's what this is going to do, right? But the fundamental problem that I still have is to figure out what this omega of phi is. And that I could just count every loop, count the number of loops in every sector I have, or I could say this coarse-grained free energy gives me the right answer. That make sense? It favors the small flux states. Okay, so this is in my very, very quick summary of the way people think about the dimer problem, which is a constrained problem. So it's a strongly constrained system, but with many, many, many degenerate states. And what we need to do then, the challenge is to figure out how to compute this in these constrained systems. Okay? And from here, you can calculate what the BB correlations are. And, you know, once I have this free energy, I can calculate everything that I want to do. Right? The partition function in this sector then is just e to the minus f. Okay, no questions? Everything's clear? Just some number. I've just divided, so it's, let's call it S. The entropy per, right? So log of omega is the total entropy, right? So I want to write log of omega as an S or a yes, which is the entropy. Yeah. Right, so I've just scaled out the N. I'm saying I don't need to, right? Sure, I can, I need to, but that's not the difficulty, right? I'm saying if X is conjugate to Q, I don't know how to define it. I don't have a thermometer to measure X. But I'm saying I could even stick to the microcanonical ensemble. I could say I fix Q, right? And then how many states do I have? So then that's the same thing as asking in the dimer problem, for example, that if I put a field that favors the large phi's, then I know that they're entropically, right? So if I want to put that, so I could just sit in the microcanonical and forget about it. So this is all about going to the canonical and the intensive parameter, which is a question. But from a stat mech perspective, I think the more difficult question is how to do this. Did Pinaki's question make sense to all of you guys, right? So this is a question, right? I don't know what this is. But if I cannot do the stat mech, I cannot even figure this out because this is some derivative of this with respect to Q. Right? So the fundamental challenge is to identify something like Q and then come up with some ways of estimating so this B, if I defined yesterday, had to do with these arrows. So in the dimer problem, I might not have written it in this form yesterday. So let's say this is a link index, and this is a site index. So these sites are at x1, x2, x3, x4, and this link index. And I can write that as and that so Ni is whether there's a dimer or not. It can be 1 or 0. So if there's a dimer here, then it's 1. If there's no dimer there, it's 0. And the sigma x, is a staggering field. It tells me that sigma x is 1 for if I am on the A sublattice, minus 1 if I am on the B sublattice. So let's see if you guys get this, right? So this is, let's say, my A sublattice and B sublattice. So A to B, so so if I want to know what Bi of x is, then sigma of x for that one is plus 1, because I'm going from the A sublattice. Ni is 1, right? Yes? So I get 3, correct? Because ZB is 4. Z is what I called it. Z is 4, right? This is a 4-4 coordinated lattice, so I get plus 3. These now are going from B to A. So sigma is minus 1. Sorry. In this way of doing it, the way I have drawn the arrows, I don't even need the sigma x, I think. So, yeah, because B to A, if I now, Ni is 0, then I just get minus 1. Okay? So B is this field which has information, but I'm always going, right? So, but if I go from, no, I do need this. There is a plus minus that I'm missing here. Sorry, I'm messing it up, but the arrows are, these arrows are fine. So this is saying there is a flux of 3. So this is the magnet, so the B field is associated with, so this is a divergence-free magnetic field. So this is the flux of the magnetic field on the lattice, right? So this is coming in, these are going out. So that's the B field. That's what I defined yesterday. And then the flux is, so if I just think of this as a magnetic field, then the flux is just that, right? And that we are saying is, does not change if I make any moves inside it. And then what I'm arguing here, very, very quickly, because is that this idea that if I have lots and lots of loops, I have many states, can be captured in a coarse-grained sense by this free energy. Because this free energy, with the divergence of B equal to 0 condition, if I minimize this free energy, I'll get the smallest flux states. So this favors small flux, entropy favors small flux. So just like, we are throwing a lot of concepts at you guys, but remember Sanath's lecture about entropic elasticity, right? Where entropy gave me some kind of rigidity to my polymers. This is basically doing the same thing. Saying the entropy is giving me some kind of free energy here. Not an energy, but a free energy. Right? But the way that I am capturing the effect of the entropy is by putting this in. Because what entropy favors, this term also favors. So here there's a well-defined way of constructing a coarse-grained free energy which looks exactly like a Coulomb gas or liquid, whatever you want to call it, because this is a B field with the divergence of B equal to 0, so this is a magnetic field. Right? There's no electric field here. It's an electromagnetism with just a B field here. Okay, and hopefully, okay, so now I do want to transition to talking about what all of this has to do with granular materials. So I'm going to erase the dimer problem for now. But remember this, that there was we identified a conserved quantity which is the flux. And that we talked about entropy. Okay. Okay, so what do we do in the granular case? And we're again looking at only mechanically stable states. So static states. Use white. And everything that I am going to talk about is in 2D. Yes. 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 Sure. Sure. So I haven't said anything in the dimer problem about factorizability, right? Oh, no. Here it's fine. There's no factorizability question here because this is the microcanonical ensemble. Well, we can come back to that. There is a way of defining it, which we have done in other, so you can define something, but it's linear in the system size. It's not, and all those questions we are still sort of struggling with in the granular context, right? So for now, let me just focus on saying how to construct a conserved quantity for the granular system and if that helps us do anything at all. Okay. So now I'll have to draw with my horrible drawing grains, and I'm going to draw them big. So one important fact to remember is that when I say mechanically stable states and I have I have only contact interactions, what matters crucially is the contact geometry, not just the positions of the grains. So I'm going to try and illustrate that by sort of trying, so even my chalk, right, has a width when I'm drawing it. So I'll try to draw, so let's say, if I Maybe from far away there, you guys think these two are in contact, but they're actually not. Right? So unless I give you these positions to sort of infinite precision, it's very difficult to figure out from looking at positions what the contact network is. So that is a real issue. But what I'm going to deal with are, what I'm now trying to construct is the analog of the lattice. Okay, so the analog of the lattice in the granular context is the contact network, and you'll see better why I'm where the analogy fails and where the analogy holds. So let me try and draw a few more. So I need to have force balance. So a question for you guys is how many contacts, what are the minimum number of contacts I need for each grain? I have friction. Right, neither of those are correct. The minimum local, for local stability, not global. I have friction. Frictionless, I need 3. 1 will not do. I cannot balance forces on a grain with 1 contact. But 2 will do. Right, I can create with friction, I can create something like this because I have tangential forces. They're extremely rare, but they can be parts of my network. But I cannot have 1, right? I cannot balance forces on a grain which has only 1 contact. Right, so this is what Bob Berenger focused on for, the last kinds of things that he did. Huh? These are Hyderabad rocks. Yes, good, yes. See, those are in force balance, right? Yeah. Okay, so that's why I was trying to be very careful here to draw. So this does not have a contact with that grain. Nothing so far. So there's no gravity, or if there's gravity, it's into the board or out of the board, whichever, okay? So I don't have any external forces, any body forces acting on these grains. It's a very good question, I should point. So I'm looking at only grains that are, let's say, sitting on this table. So their mechanical stability is only coming from the contact forces, because every grain has exactly the same gravitational force acting on it. If I want to construct a pile, if I have time, I'll talk about it tomorrow, how to do this. 2 are fine. 2 contacts are fine. But if I just put 2 grains, how can they be in force balance? How is this grain in force balance if I have only 1 force? The sum of forces have to be 0. This Newton's 3rd law. Don't confuse that with Newton's 2nd law. Yes. Right? So the force on this grain is equal and opposite to the force on that grain. Well, they can be still, but they're, right? If I have only 1 force, there's no way I can satisfy the sum of forces equal to 0. Okay? Yeah. Okay, so let me draw, because I need to draw a network. Okay, so I'm going to construct I'm going to give you a particular construction that reflects this contact network. So, okay, so I need to draw one more. So this grain has 3 contacts, and the way I'm going to represent a contact network is as follows. Okay, so I connect all of the contacts on a particular grain. Okay, so first I'm going to draw these polygons for you guys. drawn lots of threes. So I have to put in a contact here. Let me just say, I don't know what these are. I've just, okay. So what I have done now, I do need to put in something here to illustrate what I was going to illustrate. Let's say this is a very big grain. What structure do you see? So I have sort of hashed out or thatched out all of the grain, the polygons that sit inside the grain. So this space, right, this two-dimensional space, I have uniquely divided into a checkerboard pattern. It's a disordered checkerboard pattern, but it's a checkerboard pattern, correct? And every contact has two thatched and two non-thatched. So I could call them my checkerboard white and black. And what are these? These are void polygons. So I've taken the void space, the voids are extremely complicated in shape. The grains are all spherical. I've taken for here. I can take ellipses, I can take any convex shape, but now I've taken them to be spherical. But the voids are horribly complicated shapes, right? But by doing this, I've made polygons out of both. So I have grain polygons and I have void polygons. Yes, everyone sees that? And there's this particular feature that every contact where my forces sit have two adjacent grain polygons and two adjacent void polygons. Okay? So now, this complicated network replaces my lattice that we were talking about in dimers. Yes. Yes, so that's degenerate. That is a degenerate state that we have to think about very, very carefully. So the ends of that would be polygons wherever, but then they have a line. Yeah. Yeah. Okay. So now let's just think about, so what are all of the constraints that I need to satisfy? Force balance, torque balance, etc., etc. So we're going to start from just the constraint of force balance and see if we can introduce something that helps us enforce that constraint. So so let's look at this grain. It has 4 contacts, right? And those contact forces need to sum up to 0. And these contact forces can have tangential components, normal components, it can have anything that they want to. Okay? Similarly for this grain, this grain, this grain. So I'm going to introduce an auxiliary field that enforces that constraint. That sort of that automatically satisfies the constraints. And the way I'm going to do this is to first say, just like I sort of did in the dimers, I'm going to associate an orientation of these loops. So on the grains, I'm going to say that these polygons, I'm always going to make them counterclockwise. And so on the voids, they are clockwise, right? So on the grains, they're counterclockwise, on the voids, they are clockwise. And now I'm going to say, let me introduce a vector field. It's like a vector charge that circulates on these loops. So I'm going to call that. So, and these vector fields are associated with each void polygon. So if I call this H1, then H1 is circulating on this loop. Okay? H2 is circulating on that loop. H3 and H's themselves are Cartesian vectors. Because my forces are vectorial quantities, I need to keep these vectors. But in addition, they have this sense in which they're circulating. So they're vectors with a sense. So the simplest thing for me to give you an analogy is, if we had vector charges in some world, these are vector charges that go around. Okay, but these are vector fields, but they also have this orientation associated with them. Okay, so on the void polygons, these vectors are always circulating in this direction. So now, I can look at this contact. And because of the fact that I have two voids coming in, I can construct a contact force here by saying this contact force is the H that flows in minus the H that flows out, gives me the force that this grain feels. So remember, so what I'm going to impose or going to demand is Newton's second law, of where there is, now this is mechanically stable, so the forces add up to 0. And I have to satisfy Newton's third law. Right? So the force acting on this grain is equal and opposite to the force acting on that grain. So if I look at this grain, call it G, and this is G prime, right? So these are the two grain polygons that are associated with this contact. So the force on grain G prime associated with this contact C, where I'm losing these. Is going to be the H flowing in minus the H flowing out. But the contact force on G, using the same definition, what is flowing in and what's flowing out? H2 is flowing in, H3 is flowing out. So it's H2 minus H3. So it guarantees for me that I have satisfied Newton's third law. Okay, so I need this orientation to guarantee that. And also that tells me that there is this contact force is not really something I can sort of coarse grain. Because there's not a unique vector associated with this contact. It depends on whether I'm asking if the force is acting on this grain or that grain. Right? It's a funny object. Right? I can't say there's a FC. I have to tell you there's a FCG or a FCG prime. But, okay, so this is Newton's third law. Have I satisfied Newton's second law? So let's look at this grain. And all of the forces need to add up to 0. So this contact force is H2 minus H3. This contact force is, so let me now label a few more. So this is associated with this huge void, right? And this is a huge void because this is sort of a pseudo contact. It's not really in contact, right? So this has to be part of a void. Okay, so one thing here in this, for people who look at granular, there's this huge issue of rattlers, where grains are not in contact with anything. In this formalism, they just drop out of the picture. They're part of the void. I really don't need to think about them at all. They don't play any role because I look at a contact network. So if this was truly a rattler, I'd have a huge void surrounding that grain. Okay? Okay, so this contact force is H2 minus H3. This is H3 minus H4. This is H4 minus H1. So it adds up to 0. Right? So introducing these fields satisfies for me Newton's third law, and that if I sum over all contacts of a particular grain, I didn't put vectors on these, it adds up to 0. Any questions? So this is the closest this problem will come to the dimer problem. In the sense that I have these things that flow in and flow out, but for me here the things that flow in and flow out are vectors. They are continuous variables. H can take any real value, and they can point in any direction. Unless like the dimers where I had these numbers, either 3 or 1, and they could flow only along the lattice. Here they can flow anywhere along the contact, along whatever contact geometry I have. And the value, the numerical value of H can be anything. So it's a continuous field, and we will come to that. But this is only if I have ignored every other constraint, right? So I'll try to convince you either today or tomorrow that the other constraints restrict the values of H. Okay, but if I do this, this is my starting point for trying to construct something that can be coarse-grained. Okay, now the values of H will be, cannot be anything that they want to be, because the other constraints like torque balance, the Coulomb condition, enforce conditions. Yes. Yes. So rattlers, huh? So so what happens is if you pack grains, right? Because there's no thermal motion. So imagine taking hard spheres at a finite temperature and I just put it down to 0, right? There will be some particles which just happen to have no contacts at all. Right? So they fall out of the force-bearing contact network, but they're still there position-wise, right? So if in terms of positional variables, they're very much part of the system. As far as a contact network is considered, they're part of the void. So, and that's something that actually causes problems and sometimes actually helps. So tomorrow's lecture, I'll talk about a particular physical situation where the rattlers actually get incorporated into the contact network, and that's an important process. But I need to keep that in mind, and this contact network counts only, if you say, so let me put it this way, if I count the number of grain polygons, it will not include the rattlers. They will become part of the void polygons. So I can redefine the number of grains as the number of grains that are part of the contact network by just counting the number of grain polygons. So in this whole area, the really nice thing is it's completely divided into, so the volume occupied by grains and the volume occupied by voids adds up to 1, normalized in some way. Right? There are no complicated things. So if I didn't do this, computing these volumes is horrible. Right? But here it breaks it up into polygons. So this was actually, quote unquote, used originally. So I should give you references. So this formalism, which we call heights because I came from the dimer problem, were called loop forces. Same thing, by Ball and Blumenfeld. PRL, either 2003 or 2004. If you look at all of the things that are on the website, there are references, okay? But then this particular construction was sort of forgotten geometrically, and we have found it to be extremely useful in doing all kinds of things. Okay. Yes. And no, H is a field that sits on this contact network, right? But I know where the H's are. So let me put it this way. I can now erase all of the grains. I just have a network. And then H is a field that flows on this network. That make sense? H is another field that sits on top of this network. It's a vector field that sits on top of this network. To the H's. Yes, yes. Modulo, sort of global translation of all of the H's, because this is just a difference of H's. So I can add some things, because these are actually just gauge fields. So there is a global translation I can do. And but other than that, right, I can add any number to all of the H's. And that doesn't change the H's are not physically measurable variables. The contact forces are, and as you will see, the stresses are. Okay, so I can add some number to all of the H's. So the origin of the H field is arbitrary. But other than that, there is a one-to-one correspondence. So I think what you're asking, Atsushi, is if I go and come back around a long, long loop, will I come back to a unique H? And yes, that is true. Now, there's one more thing that I should mention here, that because my forces are one-sided, in the sense that I don't have any tension, I have only compressive forces. So when I said that the H can be anything, right? So I can take, let's say, this loop, this huge void loop, or maybe this one, and call that H0. Right? I can just set that H2 equal to 0, and then every H is measured from there. Now, normally, if I had both compressive and tensile forces, this is a two-dimensional vector that goes around, and I could say, okay, maybe the vector going around this one, I was trying to maintain a color code, let's see if I can do this. This vector is a two-dimensional vector, I'll just call 0, 0, right? So that's my, on this loop, I have a 0, 0, okay? Now, normally, if I had both, like if this grain could support tension, which means the force acting on this grain could have both signs, then if I go far enough away, I could find the 0 back again. Now, with purely repulsive forces, that never happens. The height is monotonic. I go around a loop, the height doesn't have to have the same slope, but the height will never come back down. So, this condition that I imposed, this constraint coming from purely repulsive forces, has a consequence that if I start from a 0 here, I'll never find another 0. in this configuration. But if I allow tensile forces, that would be possible. Which also tells you then, okay, we'll come back to that. Okay? Yes? It's different. Right, so, yeah, so if you count number of degrees of freedom, the number of contact forces I have and the number of loop forces I have are not the same. Where's Jishnu? It is not the same, right? So if you can convince yourself that if you're sitting at the isostatic point, then the heights, so, okay, and they shouldn't be the same because I have other constraints that I haven't put in. If this was the only constraint that I had, then there should have been. I should have been able to define the forces. There should have been equal number of degrees of freedom. But there are other constraints that I haven't put in. Okay, so I actually need to have, so what do I need to have? I have more constraints that I need to put in. So I need to have the number of loop variables. So the number of degrees of freedom. So what he's saying is, how many degrees of freedom are in this H field, that right? So each loop has a H, but it's a two-dimensional vector. So if I have NL loops, then I have 2 NL degrees of freedom. Yes? And how many degrees of freedom are there in my contact forces? So I have MC contacts, and there are 2 NC contact forces. Now, is there anything that I can relate? So there's NL, there's NG, and there's NC. Can someone tell me if there's a relationship between them? Think of these as edges, vertices, faces. Someone said something. Yes, which will give me a relationship between these, right? So at the frictional isostatic point, so there is this concept of isostaticity that I haven't talked about. How many of you know about this? So it's a special point. It's not going to be so important for what I do. It's a special point where the number of degrees of freedom is exactly equal to the number of constraints. So that I can determine the forces just from knowing the constraints. So at that point, you will see that the number of loops is equal to the number of grains. Am I saying this correct? At the isostatic point, the number of loops is equal to the number of grains, and then everything works out. So if you look at the Ball and Blumenfeld paper, they focus only at the isostatic point, and then they count the degrees of freedom, and at the isostatic point, this is all I need. I do need one more constraint. There's one missing constraint, which is, even leaving out the Coulomb constraint, there's still a constraint of torque balance, which I have one constraint per grain. Okay, so I can try and do the isostatic counting tomorrow. I wasn't planning to do it today. I'll do it tomorrow, and I can show you that it all works out. Or I'll make Jishnu do it. Okay. Okay, but very good question. So the number of degrees of freedom here don't come out to be the same as the number of contact forces. Okay. Now, I have 20 minutes. So what I'm going to try to do is construct the analog of the B field in the dimers. Something that has a divergence-free condition. Okay? And I'm going to do it in a way that's you might not immediately recognize as being the divergence-free condition, but if you think about it, you will find that it's true. Okay. So what I said is I cannot coarse grain the forces because there's this staggering. So I have to really so I need to have something else that comes into the picture where I can coarse grain without worrying about the staggering from grain 1 to grain, the neighboring grain. Now there is a quantity that I can associate it with each grain. I'm going to call it small phi. I'm going to call it sigma, because otherwise I'll get confused. But it's not the stress tensor. There is a difference. But let me call it sigma for now, okay? So it's a tensor associated with each grain. And I'm going to look at all the contacts of that grain. So I'm going to look at all of the contacts, let's say, of that grain, or this grain that I have drawn. And I'm going to draw these vectors. What are these vectors? They join the center to the contact point. Yes? And I'm going to call those something. We call them D. So these are vectors that connect the grain center to all of the contacts. And at each contact, there is a force. So if I take the outer product, and I should also so let me do this. This outer product is a tensor, which is a moment tensor. It's a force moment. It would be the stress dimensionally correct if I divide it by the area of the grain. But I'm not going to do that. Okay? So this has what the dimensions is length and force, right? Which has the dimensions of work, which is energy, right? So this is something that I can, if I add up all the grains, you can imagine would act like an extensive quantity like the energy. It also has the dimensions of energy. Okay, so now if I look at this quantity, and let me define, so these heights are sitting on these vectors, correct? Right? So they're not the contact vectors, they're these vectors. I'm going to call them, so let me introduce a notation. Give me each for here. I'm going to introduce a notation for an arbitrary loop to say this is the height associated with that loop. And this vector I'm going to call RLG. Is the notation clear? So this is the vector on this grain. That's a boundary of this loop polygon. Yes? Right, so I'm just establishing notation here. So these white vectors are what I called the DCGs. They're the usual contact vectors. Now in this, the way I have represented this contact network, these vectors are extremely important. These are the vectors on which my loop forces or my height sit, right? So those are important. Okay? RLG is, this is loop L. There's a height associated with that loop, and there is an RLG vector associated with that loop, which is the side of the loop that this grain is seeing, right? So this will be another RLG prime. Okay? That makes sense? Or if I think in terms of each grain, there is a R1G, an R2G, and an R3G. This grain has 3 loops surrounding it. There are 3 vectors associated with it and 3 H's associated with it. Yes? Okay, so assignment for today's tutorial, because this is not going to take you more than 5 minutes to do. Just algebraic rewriting, relating the forces to the heights and relating these vectors to these vectors, which you can do, right? They're forming triangles, right? If you do that, then I can write this particular grain quantity as a different sum. So I'm going to sum over all of the loops surrounding a grain. Okay? RLG. I'm really being messy with superscript and subscript, so ignore them. I'm not doing any tensorial things here. So this is just a rewriting which you guys should show me that you can do by today's tutorial. It's just an algebraic rewrite. So I'm replacing all of the forces. So I can tell you how to do it, right? You can write this force as sum h minus sum h prime, right? And then you can just associate it with this and do the triangle with the d's and the r's, and you'll be able to figure it out. Well, what is this doing? It's going to show us something really nice. So instead of doing that messy grain or this complicated grain network, let me just do this very simple one to illustrate what's going on. These are 4 grains. Each with 4 contacts, right? So I'm saying there's a sigma 1, there's a sigma 2, there's a sigma 3, there's a sigma 4, right? And then let me call these, I'll call this, I'm just going to put it here, but remember that these circulate on these loops. Right? So this is an H naught that's circulating on that loop. Then there is a H1, let's say, and H2, and H3, etc., etc. I haven't shown you what those voids are, but because I have a contact here, just looking at that, there has to be 2 different H's here. There's another loop here, right? Because of the way my checkerboard works. Okay, now, sigma 1 is this outer product of this contact vector times this contact vector, sometimes this contact vector, etc., right? Now let me sum up sigma 1, sigma 2, sigma 3, sigma 4. What happens? Right? So this one is H naught times this, H1 times this, H2 times outer product, I'm saying times. Yes? Now if I sum the 4, this thing is going to disappear. Right? Because it's going to have H naught multiplied by 4 vectors that add up to 0. So what is that telling me? That I take the sum of this force moment tensor of 4 grains, so it's an area integral in some sense, and it becomes a boundary term. So the sum of, so in this particular example, sigma 1, sigma 2 plus sigma 3 plus sigma 4 becomes H2 times this, H3 times this, sorry, H3 times this, I forgot some, H4, H5, H6, H7, H8, right? So it's a boundary integral. Everyone with me? Because the internal thing cancelled out. Now I can make this bigger and bigger and bigger, and all of the internal loops will cancel out. So this sum, which is like a volume integral or an area, becomes a, so this is over only the boundary of this whatever part of the system I'm looking at. I'm just going to call these RBs now. So there's RBs are these boundary vectors, outer product HB. So what does that tell me? That I can, in this example, I can make H naught anything that I want to. It's not going to change the sum of sigmas. Right? So this is the analog of my flux. So in an integral way, what I'm showing you is if I now define, I'm going to use the same notation. So flux is the sum of the force moment tensors of all grains. Now in my case here, this has to be a tensor. Right? The flux itself is a tensor because these things are tensors. But this flux I cannot change by making internal rearrangements. So if I now give me the full system, so this is, if I sum over all the grains in my granular packing, then this flux is an extensive quantity, and if I make internal rearrangements which satisfy force balance, which means I can change the H's, then it doesn't change. Right? So in this sense, I have identified my conserved quantity. Okay, so this is a force moment tensor. I'm just using the same notation as I used for the flux before. Difference is it's now a tensor. Okay, and whatever this, so if this is true, what have I shown? I have shown you Stokes, right? So the integral of sigma over an area becomes a boundary integral. So that means my divergence of this tensor is 0. Right? I have not been able to show you, and we actually haven't been able to do this, to show the differential version of divergence going to 0. What is easy to show with the height is the integral version of that. Right? If the divergence, right, so what I'm saying is, you guys all know this. Right? If divergence of B is 0, I can write B as curl of A, right? And the flux of the B field is equal to, right? So what I'm using here is to say, if I can write it in this form, then it tells me that B is divergence free. I don't have the differential version of the divergence of B going to 0. And Jishnu has been working on it, I shouldn't say struggling, because it's very difficult to come up with analogs of these differential operators on disordered networks. On a lattice, I can write down the divergence operator. But here, every contact that I have, if I think of this as a disordered network, every vertex has a different connectivity, has a different, so it's difficult to write down precise definitions of these differential operators. Okay, but it's pretty clear from the definition of the height that I can do this. So this is my conserved quantity. This is the analog of my B field, but it's tensorial. Okay. I think I'll stop here and talk about other things. So let me just mention that very recently, and I kept this open so that I can look up. There is a paper, let me write this down, and then because it really connects to, there's a recent paper on the archive by Eric D. I always misspell his name, which is called an Edwards field theory. And it's 1804.04834. So it's on the archive. It's also in phase-derived letters, it's in viewpoint, it's in everything, right? Okay, so what he did is, okay, so he assumed Edwards. But as I said, the crucial thing is to figure out what this omega of pi is, or what this, or the z micro of pi is. So he assumed the stress, right? So this is built up on things that we did a long time ago, but he used this as the conserved quantity in Edwards. So first of all, if I now think of an intensive quantity, the intensive quantity here has to be a scalar vector tensor what? It's conjugate to this tensor, so it has to be a tensor. So this is not something that, so the Edwards version of this would be to write that. This is my extensive quantity, and this is the intensive quantity. And I can write down the same kinds of things, assuming that this all works, that I can define this intensive variable as the derivative of the entropy as a function of phi with respect to phi. I have to do this component by component, etc. So what did Eric argue? Eric argued that the omega of phi, or the z micro of phi, is whatever scalar I can construct from the stress tensor and its invariant. So the simplest thing to write down is the trace of phi squared, right? This is a scalar, and it has to depend on the, so this is sort of a Landau kind of argument, but I can also do this, which is the same order in phi. Okay? So in some ways, this is the generalization of my B square. Agreed? So he just postulated this. So this is what we have, and he actually made a statement in the paper which is wrong, that we never thought about this, which is not true. We did think about it, and we put it in a paper, but that's irrelevant. So this is, what I didn't notice then, when I wrote this down, is this is the exact analog of B square. Okay? So B square in the dimer problem is precisely this, right? The B is the, sorry, it's not, yeah, here I'm writing it as the flux squared. There I was writing it as B square. Okay, I should think about it, but okay. So if I wrote this as trace of sigma squared, then it would be exactly like that. I have to go back and think about this, because it just occurred to me this morning that this is what Eric was doing. So, but a consequence of this that Eric focuses on and emphasizes is that just from this, if I just write down a field theory like this, the stress-stress correlation functions decay as 1 over r to the d. What does that remind you of in electromagnetism? It's precisely the way a dipolar field would decay, right? So what I'm saying, and this all occurred to me when I was preparing the lectures, that there is this sort of close analogy with the B square in the dimers and this here. So we haven't, so Eric didn't justify this, we haven't justified it yet, and we haven't said this is true. But what I'm trying to say is, by doing this mapping and showing that this flux of the stress tensor is a conserved quantity, the simplest thing one could propose is this. Okay, just the invariance of this. Now there are problems. The problems is we haven't taken care of all of the other constraints. Right? So those other constraints, and I'll stop in a minute, is that I haven't insisted that this stress tensor is symmetric. or the flux is symmetric, which will have to be true if torque balance is satisfied. So how do I do that microscopically, right? How do I guarantee, what constraints do I need to put on the H fields to guarantee that the sigmas that I'm constructing are symmetric? And then, if I just write down a stress tensor, the eigenvalues of the stress tensor can be positive or negative, right? So if I was looking at both compressive and tensile forces, this is probably true. This is probably a good field theory. I have to somehow now impose on this the condition that my pressure cannot be negative, or my, so how do I do that in the field theory? And how do I impose the Coulomb, the friction condition? These are all unsolved issues. But so what we are saying is there is this height representation which naturally leads to a quote-unquote conserved quantity. It's conserved in the sense that I can take all of my blocked states and divide it up into sectors. And the sectors are disjoint in the sense that I cannot do any local moves to take me from one sector to another. And each sector has an entropy that I can associate if I knew how to calculate it. And you keep asking me, so I don't exactly know how to identify the number of loops, right? If I could count the entropy. I don't know that. If we believe that this coarse-grained thing works, then we can just postulate that that's the entropy in the coarse-grained way, which is what we did a long time ago, but I was never comfortable with it. This is the simplest thing one can write down. If I just say I'm going to write down the invariance, but it's not clear to me that this has the whole physics in it. Okay, let me stop, and tomorrow I'm going to talk about an application where we have used these height fields to understand some granular phase transitions. Okay? Okay, let me stop. Questions? Okay, so let me recap. So what I showed was that on these disordered contact networks of grains, so give me a contact network. You give me a contact network and I demand force balance and Newton's third law. I can introduce these fields that circulate on this contact network edges. And that can be used to compute the force moment tensor. And this force moment tensor, because of the force balance, we knew sort of in a coarse-grained way the divergence of the stress tensor had to be zero, right? Because that is macroscopically but we need to find discrete versions of this. And what we have managed to show you is that I found the integral version of this. I don't know what the differential version of the divergence of the stress tensor equal to zero is, but I accomplished one thing, which is that this flux, which is the total force moment tensor, is now identified with an extensive quantity that cannot change due to making just local moves and maintaining force balance. If you allow me to violate force balance, then this is no longer a conserved quantity. Okay, but if I maintain force balance, I cannot change this. Okay, and these height fields, just to, there is an analog of these heights in the dimer models also. I didn't get into that. But you can imagine, because I put divergence of B equal to 0, there is a vector potential there too. Okay. Yes, Satsushi. No, because my stress tensor involves both, right? So I can change this and change that inside, right? Here, I could distort the network also. It doesn't have to be 0. It can be some number. Yes?
Yes.
if you believe this, I'm not saying any of that so far. All I'm saying is I have identified this quantity, which is a flux, and I'm saying I can change the flux either by changing RB or by changing HB. So I'm not doing the force network ensemble. I'm not saying I have to keep my contact network fixed. The flux is invariant. I can distort this, right? I can put whatever I want to in here, right? It'll always close up and give me 0, which is something that I've been saying since 2009, and people still think I do force network ensemble. The issue is that unless I do this, I cannot coarse grain. As I said, I cannot coarse grain the contact forces. The contact forces are funny beasts. By putting in this, which also has a sense of an orientation associated with it, and this, I can construct something that doesn't have this weird, it's like in the dimer, I put in the staggered magnetization, staggered field, sigma of x. I can do that there because it's a lattice. Here, the closest thing to the bipartite thing is that I have this void and the grain. And everything is going clockwise along the voids and counterclockwise around the grains. But I cannot put in a sigma like I did in the dimer problem, but I can put this in. And I can always say that the sense that I'm going around the loop is the sense in which the H's are going. So it's only when I construct this joint object that I can talk about coarse graining. So the stress tensor is the thing that can be coarse grained. There's no divergence of force equal to 0. It cannot be defined. There's no divergence of contact force equal to 0. Now, of course, you can say I can do this keeping this fixed. Then you have just reduced the number of degrees of freedom. But the flux is invariant under both. So one of the things that is no, right? Because I have to obey the other constraints. Otherwise, so this is for the experts, the H is a continuous field, right? So there's, I can put in any H field, I can make it arbitrarily small. There is no sense of a phase transition or anything, or, the flux is continuously variable, unlike the dimer where the flux changes by integer amounts, right? So in what sense can I say that I have distinct sectors of the flux, but I can do phi and phi plus a delta phi, and I go to a new sector? The point is that's not going to be true because the torque balance and the other constraints impose constraints on the height fields and the fluxes. But that we haven't figured out. I'll say a little bit about it tomorrow. Atsushi, is that making sense? Yes, sure, yes. Okay.
Okay, break for coffee and come back at 11.